Assalamualaikum and hi everyone. This is pre-recorded video 16 for chemical bonding. In the previous video, we have been introduced to hybrid orbital theory part 1. Now we are going to learn more about hybrid orbital theory part 2. Let's continue with sp3 hybridization, which occurs most often for central atom only. Okay, so the total number of hybrid orbitals is equal to the number of atomic orbitals combined. For example, 1 from S and 3 from P. So altogether is 4, right? So 1 from S, 3 from P. So 4 orbitals for sp3. Hybrid orbitals may overlap with pure atomic orbitals or with other hybrid orbitals. The hybridization in CH4 or methane, as we can see, are all single bond. The carbon atom, which is a central atom, has bonds that are sp3 hybrids. You have to label it correct. Okay, so you have to label all sp3 orbital as sp3, sp3, okay, sp3. This is compulsory to label all the orbitals, and one s here from hydrogen. This is from hydrogen, hydrogen, and also hydrogen. Other than methane, ammonia also has the same sp3 hybridization, except the lone pair of electrons occupies the fourth hybrid orbital. You can see the lone pairs here. Okay, so 1s from hydrogen here, 1s from hydrogen, 1s from hydrogen. And then you have to label all the sp3 orbitals. sp3, sp3, sp3. We now can move on to sp2 hybridization. Basically, this type of hybridization is applicable when involving double bonds. For example, it is comprised of 1 2s orbital and 2 2p orbitals, okay, to produce a set of 3 sp or hybrid orbitals. So we start with ground state here. This is a general orbital diagram. So 2s2 and 2p1 here. 2s2 and 2p1 as a ground state. So in excited states, one electron from the 2s here actually get promoted to this orbital. So this is excited state, and then the hybrid states, sp2. So one from s and the other two are from p. So leaving an empty 2p orbital, which is remains unhybridized. So this is hybrid state for sp2. For sp2, the geometric distribution of the three sp2 hybrids orbital is within a plane directed at 120-degree angles. So you know that the distribution gives a trigonal planar molecular geometry as predicted by VSEPR. Okay, so you get a blue things like this from combination from 2p, okay, and 2s here. For sp hybridization, this hybridization scheme is useful in describing triple bonds. Okay, the geometric distribution of the two sp hybrid orbitals is on a line directed at 180-degree angles, so it is linear. You can see, so this is from p, and then this is from s. Only one green loop representing p orbital and red circle representing s orbital combine to form a sp hybrid orbital, which is linear. So it will look like this. Let's take a look at hybridization which allows expanded valence shell, for example phosphorus or any other elements in group 5a, as 3s electron can be promoted to a 3d subshells. Okay, so this 3s from here can be promoted to 3d subshells, which give rise to a set of 5 sp3d hybrids orbitals. So this is 5 altogether. So this is sp3d orbitals. So now sp3d orbital is formed, which consists of 5 loops. It can overlap with another orbitals from another atom to form molecules or compound. You can see here, it contains actually 5. 1, 2, 3, 4, 5. This is another case for group 6a element, for example, sulfur. As 3s and a 3p electron can be promoted to the 3d subshell, which give rise to a set of 6 sp3d2 hybrid orbitals. When sp3d2 orbital is formed with 6 loops, okay, 1, 2, 3, 4, 5, 6. Okay, so meaning that this central atom can be bonded with other 6 atoms. So this orbital, it can be bonded with another atoms like hydrogen or fluorine. That is the end for hybrid orbital theory part 2. Thank you and see you in the next video.